Okay, let's get going. So, morning everyone. Hello. Thanks for coming. It's really great to be here. And I think what I'd like to talk about today is a really fun project that we've been involved in over the last year or so. And really, the project is built around how do we create scientific compute platforms on federated OpenStack infrastructure, so across multiple sites, multiple deployments. How we create those, what they look like underneath. So I'll dive in. So I represent a very small company based in Bristol in the UK. You won't have heard of us unless you also work in the small niche that we work in. So, but the history, I first met my colleague and co-founder John in 1992 when we worked together in a company called Mako. And since then I've worked in a string of other interesting and performance-oriented roles in Alpha Processor, Quadrix, and Nodal, Cray, and then we founded StackHPC based on and building on a lot of that experience. So StackHPC knows OpenStack, and our expertise is really focused on how to make it work well for high-performance computing and big data environments, and that's the company in a nutshell. So OpenStack, the interesting piece there for science is that it's really become the de facto means to bring cloud interfaces and methods in-house for research computing infrastructures, and it's complex, and everyone knows it's complex and feels it's complex, but that really is because the sort of the vision and the scope of it, the ambitions are so all-encompassing in terms of bringing private cloud to environments. So I guess that the first thing that the skeptical high-performance computing or research computing administrators look at when they see OpenStack is what on earth is this big layer of fat between my workloads and my hardware, and why on earth would I want to have that? So I guess that the selling point, there are many advantages, but the major one to cover today is that actually now we have this idea that we can create environments which are dedicated to a diverse range of workloads. So we can, in a one pooled infrastructure, we can specialize it in different directions at the software level. And this really maps well to universities or broad research computing environments where there may be many domains of research, there may be vastly different software stacks, largely different expectations of how to use them. And the cloud method really easily creates software deployments that are tuned to each of the domains of research or activity within the institution. So that works very well, and it also enables us to, in a research facility, we can share and we can isolate. And OpenStack provides mechanisms for self-serving custom software stacks, but also controlling how the data is shared within a group and isolated between groups. So it has a number of compelling advantages for those use cases. But if we were just to recreate the software environments of today on the next generation cloud infrastructure, we're kind of having a loss of imagination there. So what we need to be able to do also is to create a bit of diversity. And so the first phase of cloud migration might be to recreate the same environment, only not quite as well. And then when we get the vision of what we can actually do with this flexibility, how we can build on it, and we start to bring in other kinds of environments. So we can run data analytics environments as well as conventional high-performance computing environments, as well as containers and the container infrastructure of Kubernetes. So there's a kind of a popular emerging use case around this kind of model, this paradigm, where we might run OpenStack next to a highly tuned, batch-oriented high-performance computing system, which would be optimized to a compute-intensive workload. But then we'd run OpenStack as almost like the second car in the garage, in that it's doing the data analytics in order to feed the high-performance computing resource and then digest the results coming out of it. So then we have this nice cycle in which we have two pieces of consolidated infrastructure, one of which is oriented towards flexibility and the other one is oriented towards raw performance. And that works pretty well in a lot of use cases. But OpenStack's party trick is this one. How do we always have this assumption that cloud performance comes at a performance price. And that really doesn't have to be the case, because now we have this kind of continuum between performance and flexibility. And OpenStack's diversity and its flexibility of configuration enables us to really choose how we can build it and what kind of trade-off we get in terms of the overheads of performance versus the convenience of cloud-native flexibility. And this is OpenStack's party trick, in that what we can do is do away with all of the virtualization overhead and spin up a bare metal compute cloud. And so therefore we have no layer of fat between the two, and we can still run a broad range of workloads and platforms on top of a common piece of infrastructure. What is nice about this is that a performance cloud like this, one which is fully at one end of that continuum of convenience, is still way more flexible than anything else that's out there in terms of research computing infrastructure management. So this is quite an interesting balance which is being struck, and this is where the disruptive change is coming from OpenStack environments in research computing. So one of the emerging capabilities that is really a testament to this is this idea that actually when we have high-performance computing workloads and we have data analytics workloads on the same system, what we can do is we can actually rewrite the configuration in the BIOSes when we are booting an instance of one type or another type in order to optimize a consolidated general-purpose hardware in order to make it tuned for straight-line speed, no hyperthreading, and sort of raw performance and low latency in one direction, or high concurrency, no RAID, and throughput-oriented configuration in another. So that if we're working on high-performance computing or high data-intensive analytics using Hadoop, we can actually specialize the general-purpose computers that we're using in order to tune them for one use case or another. And we can do that in service of every single deployment. So whenever a new node is configured or booted in service of a user, it will be optimized for their use case. This is a term that we're somewhat pretentiously calling the software-defined supercomputer, given that it enables, in a service of software-defined requests, we can actually optimize the whole thing as far as we can on a general-purpose resource. So this is work that's really emerging at the moment. And if you're interested in seeing a bit more about it, my colleague Mark is going to be speaking about this work at the OpenStack Summit in Denver in about a month's time. Really, it embodies the aspiration of everything that our company hopes to achieve in terms of bringing OpenStack and high-performance computing into one converged use case. So the proposition of how we software-define infrastructure looks a little bit like this. High-performance computing in cloud environments is really a combination of the best bits of both worlds. So we're using cloud-native methods and tools, but we're provisioning high-performance computing infrastructure and platforms upon it. So then we start to bring in nice components or good components from each of those environments in order to create something which is enriched. The other nice piece about this is that we get a better service and better experience for our end users, and also a nice diversity of use cases. But we're looking at one which we're going to be focusing on in this talk, which is about how we create an environment based on batch-queued compute, but then we start to try and bring in other pieces. So we have Slurm, which is the batch queue environment, but next to that is the OpenStack service Manaska, which delivers user performance telemetry, logging, and analytics. And so then we can actually gather data from the workload environment and serve it back to the user in terms of dashboards in a very easy to use and very friendly way. We also incorporate parallel file systems such as BGFS. And in an environment where we can bring together HPC-oriented hardware and cloud-native software, we can also use things like high-performance computing technologies like remote DMA and high-performance fabrics in order to use things like InfiniBand and other technologies to give a really high-performance environment, but it's all very familiar to a cloud-native context. So this is all delivered by interacting with the OpenStack APIs and using tools like Ansible in order to then, once we've talked to the APIs to build the infrastructure, we then pave the platform upon it. And actually, that's how we deploy OpenStack in the first case as well. So the whole thing is turtles all the way down. And right at the bottom, we have things like configuring of our network switches, the RAID controllers, the BIOS is the firmware, the iDRACs and ILOs and those types of things. And then we start to define our data center in terms of source controlled infrastructure. And that really builds up some powerful things. So now we can start to talk about configuring network switches and BIOSes using Ansible, for example, and then deploying our operating systems, our storage clusters, and our container runtimes also using Ansible. And then deploying the user workload. So we deploy the VMs in service of various flavors of compute platforms, OpenHPC, CentOS, Ubuntu, Fedora Atomic for Kubernetes environments, and then start to build up the platforms on top of it. So we might talk about batch-queued environments, particle physics, high-energy physics environments, data analytics, containers, that kind of stuff. The whole thing from top to bottom can be configured and orchestrated using the same paradigms. And that's really, really powerful. One of the areas where we see some really a sort of huge potential and bright future is this idea. At the top we have Jupyter notebooks, and using those as the user interface creates a very nice sort of explorative environment for doing data analytics and for generally for interacting with high-performance computing hardware, but in a very native and intuitive way for scientists and end users. So Ansible shows up a lot there. I think everyone is probably familiar at a conference like this what Ansible is for and what it does. The major point I would say is that it's not a programming language. It's not a work of art. It's just a nice toolkit which is very useful for solving problems in deployment and configuration management in ways which are just very convenient to get using. So the way that Ansible is used in order to build our platforms is we start to make these compute clusters, and we define them as infrastructure, and then we configure them using Ansible. And the way that we're working in this project is really about how we have pre-configured or reserved allocations. So we're not talking about spot instances or opportunistic usage. We're talking about a system in which we make a reservation for 1,000 cores for 2 weeks, we use it, we make a cluster, we boot it, we run it, and then the thing gets packed up afterwards. So this actually ties into a problem or a disparity between the cloud world and research computing, in that in research computing we really want to fill our machine, and in the cloud world we want to hide how full the machine is. So the public clouds will never tell you, oh, we've got 1,000 spare VMs right now, or some such thing. They will always work to conceal that, whereas in a research computing environment, we have to maximize the fullness of the system and demonstrate that as being one of the metrics for the overall performance of the infrastructure. So this is somewhere where more work needs to be done in order to take this concept, which is deeply buried in a public cloud, and expose it as much as we can in the private cloud.
So actually, if you're operating in public cloud, you want to sweat your assets because you're paying for those. You purchase those Intel CPUs.
Yeah.
Money from them. So the customer, you hide it from the customer, but you actually want to keep your utilization as high as you can without degrading service. So that's a customer first.
Yes, yeah, that's very true. Yeah. So we're going to focus on the case study of what we were doing. First of all, I doubt everyone knows what Slurm is. It's just like the green screen VT100 forerunner of the Kubernetes job API in some ways. It is a batch queued job processing environment which turned up around 96 or so. It's used particularly for parallel computing workloads. So it's not an interactive thing. We define a job, we run the job, the answers for the job come back, and but it's not a iterative, interactive, responsive kind of environment. It's about running parallel workloads in a batch queued environment as efficiently as we possibly can. So a Slurm cluster typically has a couple of things in it, schematically, in a very naive way, it is some login nodes and some compute nodes, and that's really the level of detail which we need to go into today. The way we can define this in a platform is using YAML, which is sort of the native data format for Ansible. But conceptually, we should just think of it as groups of compute resource, and named in particular ways with particular purposes associated with them, which are not defined in the infrastructure but become important for the platform. So this is the output, and there's nothing really to say about that. So we start to build our compute resources upon the infrastructure. So once we've booted the nodes, they're essentially useless, but they've got the right names. And we start to build in this environment where we can pull in things like a fabric technology like InfiniBand, user authentication processes, bringing in sort of parallel file systems and other things, and really starting to make a formulated deployment of a actually usable cluster environment. And that is where we take a small diversion into some hardware, in this case, the Euclid Space Telescope. I'm not involved directly in the Euclid Consortium, but we've been working with members of the consortium in order to do simulation work for this telescope, which hasn't been launched yet. It will be launched in 2020. But various institutions in the UK are responsible for some major areas of the mission. And in particular, we've been working with a group from the Edinburgh Royal Observatory on developing weak lensing algorithms which underpin the theory of the mission's purpose. So this is gravitational lensing and using it in order to infer the existence of matter, or dark matter and dark energy. I don't know much about it, but the Euclid mission's purpose is in order to identify the matter distribution across the universe as approximately as we can, and then use that in order to infer from the gravitational shearing, or the cosmic shearing of distant galaxies, what is going on in the foreground, in order to understand the difference between what we perceive and what is actually happening in effect. The systematic effects have to be properly modelled in order to understand whether the theory can be applied, so that we can, with knowledge of some of the foreground matter, we can actually infer from the sheared images that we see of distant objects whether there is something that was not accounted for. That's my understanding of it. I'm not going to answer any questions about it. But actually, in the fundamental, in the computer science side of things, they want to use a Slurm platform with some extra pieces in it as well. So creating Slurm appliances, as described, is we don't really want to do a one-size-fits-all because we have the freedom to explore, and we have the freedom to define how this service is built up. So we take a Slurm environment, so this batch queued environment, and we build other things on top of it. And so we can add extra software packages into the stack, and we can bring in extra file systems and extra data services like the data protocols that are used in CERN, and generally bring the whole thing together into an environment which is rich and familiar to the team working from Euclid, but managed in a very dynamic and flexible way. We had a very interesting opportunity when the Cambridge University renewed their high-performance computing infrastructure, so their main research and computing environment. And we got access to 600 nodes of slightly old hardware, but with InfiniBand and Lustre and other performant technologies integrated with them. And we had a couple of months or a few months in order to use this system before it got replaced in the data center So we've spawned upon it a bare metal OpenStack environment and used it to make Euclid-as-a-Service. So we had about 500 nodes of the 600 in the system available to us, and we built a very large Slurm-as-a-Service, but then integrated it with other pieces, also using Ansible and other components, to the research data storage, the Lustre file systems, local Ceph file systems, and other such things. It wasn't perfect, given that it was all slightly old, cranky hardware, but it ran for 30,000 core hours and enabled the Euclid team to do 13 simulations of their sky survey with different values for instrument effects, background noise, and other things, enabling them to refine their model to measure the effectiveness of their weak lensing algorithms. Looking ahead, so this ran from September of last year for a few months, and then we started to build on this. So we're now introducing this new research computing federation known as IRIS, which has just started. This is into its first year of sort of formative operation. And I think we'll probably hear a little bit more about this in other talks today. But this is the UK Science and Technologies Facilities Council, who produced this idea about federating pooled resources from different cloud or different private cloud environments across the UK science network. Our role in this has been to create a sort of a common portability environment, which we've been rather grandly terming Scientific OpenStack. But the idea is that across many sites, so here we have 4, we have Edinburgh, Rutherford Appleton, Cambridge University and Manchester University. Conceptually, we can bring in a larger deployment of available capacity from these different private clouds and create a single compute resource which is coherent and but it is still federated and remote. So we get 4 infrastructures where we have a sort of a command and control login facility at Edinburgh University, local to the scientists, and then batch compute facilities which are using resources across 3 other federated sites. So conceptually it might look like this, with the purpley diamond mesh in the middle being a large sort of VPN mesh between the different sites. That enables Slurm's job control and cluster membership and these other things, but actually then we also need to be accessing data, so we don't pull that across this VPN mesh because that would hurt quite a lot. We use CERN VMFS, which is a method of distributing data from central repositories using HTTP, and then where it is available, we also integrate high-performance local storage technologies. And this solution then creates what we call the illusion of proximity, which is this idea that it looks like it's one coherent resource, but we try also to, and it does work as a coherent resource, but we try not to hide the locality and the remoteness of the different components, because if we were to completely work in defiance of that, it would be very slow indeed. Finally, as part of this, we can also work with a Ceph cluster and create a federated file system, and this is where the current research activity is going on, so that we can have local storage and local regions within the file system, and then also have access and visibility for to the remote regions of the file system in case there is data which needs to move across. Now, this federated appliance is really very much following what you might call the sort of the Conway's law, in that the way that the data and the networking are configured is to minimize data movement across the federated links, and really it's really structured around the way that the application thinks. So these kinds of applications where we might want to be exchanging large amounts of data between the different sites may well need a different solution. What we have here is really oriented around the nature of the application that is being run in this environment, the workload environment, in order to serve it as well as we can. So we have localized compute and then remote visibility of the other pieces for the times when small amounts of data is exchanged between the different sites. So ultimately, what we're looking at is creating a single cluster which looks like it is a bunch of compute partitions which are close to each other, but actually they're spread across the country. But logically, they're able to speak with each other, and they're created and configured according to the resources available to each of the different sites. And we have locality-aware federated cluster file system, which kind of presents this sort of logical substrate, which is fast for the local accesses, but works for the remote ones too. And I hope that was the right level of detail. Thank you very much. I'd particularly like to thank, in fact, Alex is there, and Mark Holliman at Royal Observatory of Edinburgh, and our team. So, thank you very much. Yes, so CERN VMFS is an HTTP file system, and what it does is you have one writer, essentially, who would then sort of publish data to a central repository, and then there is a network of squid caching and other things which will enable the efficient dissemination of a read-only data set or application from one place to many. So this is how the CERN computing grid, for example, will be distributing code and data across many sites, across the different Tier 1 sites.
You mentioned the heat template for standing up virtual machines and things. I was just wondering, the actual hardware, I'm sorry if I missed this bit, I was trying to find which one was which, the network stand-up. How do you interact with the network, and do you have any special Ansible playbooks to define the network configuration? Do you run like overlay networks per tenanted project, or how does that work?
So those are the kinds of questions which are sort of site infrastructure questions. And we do run tenant networks for each of the sites. And when we're talking about, essentially there is a localized network which could well be the sort of InfiniBand and high-performance networking for communication within the partition at one particular site. And then the second tier of the networking is a layer 3 route across to another subnet at another site, and those are managed as a VPN mesh. Does that cover the question?
I was just wondering, is that part of this project? Are you ripping down and standing up new network segments as part of this, or are the network segments static with the workload dynamic on top of it?
Yes, we typically reuse the networks from one deployment to another. So, but I mean, there's no reason why you couldn't actually create the networks as part of the heat stack. But generally, we follow this policy where if there is a network already in existence, then it's quite easy to make use of that. And actually, that may actually be what people want in terms of creating the right kinds of data sharing. There may well be other appliances involved in the thing.
No more questions? Thank you very much.